Chapter 21, the kinetic theory of gases. We have so far studied the concepts of temperature, heat, and so forth. We know in thermophysics we study the properties of both materials, such as a tank of gas or a tank of water. So far, we have not studied the fact that these materials are made of individual molecules, actually a large number of such molecules. We just focused on the so-called macroscopic quantities. Macroscopic. Macroscopic means these things are large enough for us to see, such as pressure, temperature, volume, and so on. Those quantities are large enough for us to measure macroscopically. We focus on the relationship between these microscopic quantities. And this way of studying thermophysics, studying both materials, is called thermodynamics. So in thermodynamics, we do not look at the molecular nature of the properties. Rather, we focus on the macroscopic relationship of these quantities. But you know, the physical properties such as the pressure, temperature, volume, these things are rooted in the microscopic nature of the substance. Microscopic. That the speed of a molecule, the mass of the molecule, all these things really have to do with how much pressure a tank of gas can exert. So, if we look at the microscopic root or the molecular root of these macroscopic quantities, then we need to establish a bridge that takes us from microscopic to macroscopic. Okay? That is, we start from the molecular nature of the substance, such as the mass of each molecule, how fast do they move, that sort of thing. And from these quantities, we can calculate the pressure, the temperature, and so forth. Now, being able to do that allows us to have a deeper understanding of the physical nature of these quantities. Of course, you can see this is usually not easy to do because, you know, there are so many of these molecules and each of them is so tiny. How do you use the properties of molecules to find something much, much bigger, such as the shape and size, such as the pressure, the temperature, and so forth? We have to establish this bridge, right? And this bridge, which takes us from microscopic to macroscopic, we call it statistical mechanics. Okay? And the key term here is statistics. That's why we call it statistical mechanics. This chapter will give us a glimpse into the idea of statistical mechanics. We're going to focus primarily on the simplest system there is, and that is what's called ideal gas. So that's what we study, what's called kinetic theory of gases. Okay, now let's look at the special nature of the system we study. We're looking at, say, a tank of gas, okay, or a bottle of water. It's a piece of bulk material which is made of a very large number of individual molecules. What's a typical number? Well, we've all heard of what's called Avogadro's number. What's Avogadro's number? That is the number of carbon atoms in 12 grams of regular carbon, which means carbon 12. And that number turns out to be 6.022 times 10 to the 23. So the order of magnitude is 6 times 10 to the 23. We know it's such a large number, right? It's 10 to the 23. That is 10 trillion trillion. Now, how big is 10 trillion trillion? It's very big, but let's use some idea to figure out just how big it is. Okay, so we have some idea about what kind of problem we're dealing with, what kind of large number we're dealing with here. Let's say now, we have all these molecules, right? We have all these molecules. We have this many molecules, okay? And each molecule, in principle, satisfies Newtonian mechanics, okay? So, you know, given their velocity and position at a given moment, I can use Newton's second law to figure out, based on the molecular forces, I can figure out where they're going to move, how fast they're going to move, and so forth. So I can predict whether this molecule is going to collide with that molecule, and so on. So everything, in principle, can be determined from Newton's second law. Okay. The question is, given this many molecules, is it practical for me to use Newton's second law to solve all these equations? All right, you know Newton's second law is a three-dimensional equation. So really, it's actually three equations combined: x direction, y direction, z direction. But let's say, for simplicity, let's say each molecule, I only need one equation, one vector equation in all three dimensions. Okay, now you need to write down 6 times 10 to the 23 equations. Of course, a single page is not going to fit it, right? Actually, 1,000 pages is not going to fit it either. You need a lot of pages in order just to write down these equations. I'm not even talking about solving them, okay? Just to write down these equations. I want to do an estimation here. I want to know just how many pages do you need to write down these equations. Okay, now let's see now. How many pages do we have in our textbook? Oh, our textbook has about 700 pages. Okay, 700 pages. Let's be generous. Let's say our textbook has 1,000 pages. Okay, 1,000 pages, 10 to the 3 pages. Now each page, let's say we erase everything from this textbook. Okay, make it all blank, and rather we fill in the equations, all these equations. And let's say we can write equations very, very small. How small? We can squeeze every equation into the size of one letter. Okay, just one letter. I don't know how you do it, but suppose you have the ability to do so. Okay, how many letters do we have on each line of this book? Well, let's say how about 100 letters? All right. So how many lines do we have per page? Well, it's actually more like I don't know, maybe right around 50 lines. Okay, so 50 lines. Let's say, be generous. We have 100 lines, and each line contains 100 letters. So we can convert these 100 letters to 100 equations. So we have 100 letters per line. That's 10 to the 2. Plus 100 lines per page. That's another 10 to the 2. So 1,000 pages, right? So it's 10⁷. That's 10 million equations we can squeeze into this book if we manage to erase everything and put such tiny, tiny equations, one of the size of each letter in this book. But that only gives us 10 million equations. That is not even close to 10 to the 23. All right, so we say one book is not enough, right? How many books have you ever read? All right, have you read 1,000 books? Well, probably not. Most of us probably won't read that many books in our entire life. But let's be generous. Let's say you read 1,000 books. Okay, so that's all the books you've ever read so far. We erase everything from these 1,000 books and just put in these equations. That will give you another 10 to the 3. Okay, so that brings the total number to 10 to the 10, which is 10 billion, a very large number, but it's still not quite 10 to the 23. All right, how about this? Let's erase every single book ever written on this planet. Okay, erase everything. Just put these equations instead. Put these tiny equations instead. Now the question is, how many books do we have on this planet? Well, I don't think anybody knows for sure. But let's be very, very generous. Let's say we have 6 billion people on this planet, right? Let's say every person read 1,000 books and they're all different. Okay, now that of course is way too optimistic, but let's just pretend that we all like reading. Okay, so we have 6 billion, right? Billion is 10 to the 9. So you got 6 billion people. Every person read 1,000 books. Erase everything, every single book, every single line, every single letter, and put in these tiny equations. What do we have here? That is 6 times 10 to the 19, right? That's 10, that's 19. You see, that is still a lot less than 10 to the 23. There's still a factor of 10 to the 4, which is 10,000. In other words, one Earth is not enough. We need 10,000 such planets, full of people who like to read. Erase all of their books and just put these equations in. That is ridiculous, of course. So what did that tell you? It is impractical just to write down these equations because there's so many of them. Okay, let alone solving them. What does that tell us? Even though each molecule can possibly satisfy Newton's second law, it is impossible for us to use Newton's second law and solve the equation of motion of each and every one of these 10 to the 23 molecules, because there are just way too many molecules. Okay, so this is different from what we studied in physics 1A. In 1A, we study maybe one particle or maybe two or three particles connected together. We were able to actually follow Newton's second law to figure out exactly how each particle moves. I don't think we can do that anymore because the nature of the problem has changed. We have this many molecules to deal with, and therefore we must invent a new way of doing things. So what is the primary difficulty of our task? Well, it is that we have so many molecules to deal with. For example, look at, if you imagine a number of air molecules in this room. Okay, we're not talking about just one mole. We're talking about many, many moles. And typically, I would say 1,000 moles easily. Okay, that would be 10 to the 23, right? That's even larger. So you face a problem of 10 to the 23 molecules. The sheer large number, 10 to the 23, 10 to the 26, makes it impossible for us to trace each molecule using Newton's second law. So, how do we resolve this problem then? What's the new thing we must invent? Well, sometimes where the problem gets the most difficult is also a hint to where the solution might be. You see, we have this many molecules, right? 10 to the 23, 10 to the 26, whatever. Since we have that many molecules, each molecule is not very important anymore, is it? I mean, if you have Newton's second law, and if you look at, two objects pulled together with a string, say they have about the same mass, and if you take one object away, of course, you cut the string, of course, when object's cut loose, immediately the problem changes, right? The solution also completely changes. But you have that many molecules, okay, 10 to the 23 molecules, all these air molecules in this room. If I take away an air molecule, would you know it? Of course not. If I take 1,000 molecules, 1,000,000, 1,000,000,000, or even 1,000,000,000,000 molecules from this room, would you know it? No, you wouldn't know it at all because the pressure, the temperature, the volume would hardly change. There's no way we can notice it. So, that tells us that because of the very large number of molecules, I don't know how to figure out the equation of motion for each molecule and solve it. But on the other hand, precisely because of the same reason, very large number of molecules, I don't need to do that, do I? Because I don't need to know detailed knowledge of each molecule, how they move, because each molecule is not that important. Okay, so here is the idea. What is the key idea? What is the key idea? The key idea is that since each molecule is not very important, what I need to know is not how each molecule behaves, rather I'm interested in the average value. For example, you look at the molecular speed, right? Some molecules are going to move fast, some are going to move slow, right? It is not quite necessary for me to figure out how fast each molecule moves. What is really important for me to figure out is what is the average speed of each molecule. Now, this is something that can affect, for example, the room temperature, the pressure, and so forth. So we're looking for average values. Okay, we're not interested in the detailed knowledge of each individual molecule. Rather, average value is good enough. But the thing is, how do we obtain average value? Well, this is achieved by doing what's called statistics. We perform statistics, and then we will obtain the average value, which has direct consequence on the macroscopic quantities that we do care about, such as pressure, temperature, and so forth. So this is the key idea. We are going to do statistics to find the average value instead of focusing on each individual molecules, which is impossible and not necessary. Okay, this is why we're going to study the so-called statistical mechanics, because we do statistics. So let's take a look at an example how we implement this idea. Again, the system we study is a bulk material which consists of a very large number of molecules. Okay, now there are different ways the molecules to congregate depending on the intermolecular forces. That actually can result in different phases, right? You have solid state, you have gas, you have liquid, and so forth. We're looking for the simplest system first. Okay, the intermolecular force, if they're very strong enough, we form a solid, right? If they're very weak, we form a gas. If they're somewhere in between, you have what's called a liquid. Okay, the intermolecular force is typically complicated because they can turn from attractive, repulsive, and so forth depending on the distance and the temperature, and therefore, if we have a choice, we'd rather try to avoid it. So the idea is, if you're looking for the simplest example, the simplest system, then you're looking for a system where the intermolecular forces are very weak. So even though they're very complicated, I don't have to worry about them too much because they're very weak. Okay, that immediately calls for the gas phase. Okay, the reason why something is a gas is because the intermolecular force is weak enough. But even in a real gas, even though it's a gas, there is still intermolecular attractions. Okay, in fact, if there is no intermolecular force whatsoever, the gas molecule will never condense at low enough temperature to form a liquid. And yet we know gases can be liquefied. They can even turn into solid when the temperature is even lower. It's just that the intermolecular attraction is weak, so that you have a gas state. Now, is there a way we can make this even simpler? And the answer is yes. We can study what's called an ideal gas. There is no such thing as ideal gas in the real world because nothing really is ideal. So what's an ideal gas? Well, the reason we call something a gas, again, is because the intermolecular forces are weak, right? So how about, since it's already very weak, how about if I make a further simplification? Let's say, let us simply ignore the intermolecular forces. Okay, so we just completely turn off the intermolecular interaction so that the molecules do not attract or repel each other. There is no intermolecular force. We call it ideal gas. Now, let's be very careful about that. We say there is no intermolecular force. So we have one molecule here, another molecule there. Okay, they do not see each other at all, right? They don't see each other at all. But does that mean they were never colliding with each other? Well, of course they do. They can sometimes bump into each other, right? Now, when they do bump into each other for a very brief moment, can I say that there is no collision between them? There is no force between them? No, I obviously cannot say that, right? So therefore, when we say there is no intermolecular force, what I mean is when the two molecules are not in collision with each other. But if they do bump into each other, okay, there is a collision, right? So it bounces over there and this guy bounces this way. We must allow a brief moment of interaction. Okay, so we can think of each gas molecule as a tiny, tiny elastic ball. Okay, when the balls are not touching each other, and when they're not in contact with each other, there is no force between them whatsoever. Say when one is here, one is there, they don't see each other at all. But for the brief moment, and when they do make a collision with each other, then there will be a force between them which allows them to move separate ways. This is how they can transfer energy from one to one another. But let's, for simplicity, assume this collision is elastic so that the total mechanical energy of the system is conserved. Okay, also, each molecule can also strike the edge of a container, say, the side of a bottle which contains the gas. And when they collide with this wall of the container, the collision is also elastic. Okay, so basically, imagine we have a whole bunch of very tiny elastic balls. Okay, they move in straight lines because there is no force between them unless they hit each other or they hit the wall. In such an event, they will just make an elastic collision with each other or with the wall. Okay, so if you look at the internal energy of this system, okay, of this n particle system, you have, of course, the kinetic energy of each molecule, right? What about the potential energy? What about the intermolecular potential energy? Well, you know the potential energy has to do with intermolecular force, right? And we say the force is zero, except for the brief moment of collision. Therefore, we say we don't worry about intermolecular potential energy. There is no such a thing as intermolecular potential energy if it's an ideal gas. So the ideal gas, when it comes to internal energy, there is only one thing associated with its temperature, and that is its kinetic energy of molecules. Okay, and also we assume that even though the gas molecules do bump into each other, the intermolecular distance is much greater than the size of each molecule. Now this is necessary because if each molecule, if the size is comparable with the distance, then due to the nature of the molecular force, the force between them cannot quite be neglected anymore because at that distance, the attraction or repulsion is not something we can ignore. Okay, so basically we're looking at a fairly dilute gas, if you will, because the intermolecular distance is much, much greater than the size of each molecule. So this also tells us how we can turn a normal gas to ideal gas, at least approximately. Okay, if you look at a tank of normal gas, how do you make the property of this gas very close to ideal gas? What you can do is you can increase its volume. In other words, you dilute it. Okay, that decreases the intermolecular distance, which reduces the intermolecular force. Okay, the force is almost equal to zero, except at the event of a collision. Then we have what's called an ideal gas. Now, is the ideal gas a good approximation or bad approximation in the real world? Well, it turns out that for most gases that we are interested, such as air at room temperature, okay, the ideal gas model is an excellent approximation. Very, very good approximation. In fact, we'll be doing experiments involving air at room temperature, and we're going to assume it's an ideal gas, so we can apply the so-called ideal gas law to it, and to see whether it agrees with the experiment. And the agreement usually is very accurate, which means the ideal gas is not just a simplification, but it's a good one. Okay, it does not change the fundamental features of the problem. So that is what's called an ideal gas. And what we're going to do right now is we're going to use the ideal gas model, okay, to study something that we can measure directly, and that is pressure. Using this, we can get an idea how to use statistics to find the average value of a microscopic quantity, such as the speed and so forth, and we use that to figure out macroscopic quantities. Okay, so again, we go from microscopic to macroscopic using statistics. This is the idea of statistical mechanics, and we can look at our first example of just how this works.